Okay, very good. Well, first of all, thanks to Pusha, thanks to the judging committee for your volunteering your time in this effort. This is joint work between our team at IBM Research and UNICEF, both UNICEF in New York and a team on the ground in Uganda. A quick outline. I'm going to give you some background about the actual project and what we've done in Uganda. Talk a bit about methodology and accuracy, the performance, the way we deployed it, and some of the societal impact that we're now seeing in Uganda. So this is the basic idea of a system called U-Report. It was developed almost 3 years ago by UNICEF, and basically it's an open SMS platform that has been designed to give community members in Uganda a way of communicating what they feel and what they see and various observations about life in Uganda. A couple of comments. It's commonly used by young people. 60% of the people, the population in Uganda is 21 years or younger, and very, very few people in Uganda have traditional computers with internet access. So their common mode of communication is a cell phone, not necessarily a smartphone, by the way. So UNICEF recognized this and basically provided a platform where they could join by texting join to a specific number, and they could then use the system in two different ways that we'll be talking about here. First of all, periodically, almost once a week now, UNICEF will push down a survey to all of the U-reporters. By the way, there's now over 250,000 of them in Uganda, and they will respond. You'll see a result of that in a moment. But more notably, what kids decided was that all of a sudden, for the first time, they had a way of communicating with UNICEF in Uganda and other governmental agencies in Africa, and started using it much like people might ideally use Twitter. That is, they observe things and they tweet it, or in this case, they text it. So it's an interesting system. It's an interesting societal innovation, and our contribution was bringing needed text analytics to help the system perform even more reliably and drive deeper impact. So here is one of the survey topics. If you can read it, you can see the gravity of the situation that we're talking about in Uganda. Have you heard of any children being sacrificed in your community? Tell us yes or no. Alarmingly, 37% of the responses were yes. You can see a map colored here of Uganda so that immediately UNICEF can understand where this is happening. Now, what's happened, as I suggested, in light of this survey mechanism, is all of a sudden kids started just clogging the channels, if you like, with all kinds of observations. Some of them, as we've seen in a moment, quite disturbingly. And UNICEF was faced with a traditional information filtering problem, namely, how do I deal with now up to 30,000 unsolicited texts? That's what we refer to, a text that comes in, directly from the user as opposed to a survey response. And how do I find the perhaps 6% of those messages that really matter and filter them to perhaps not examine the ones that require less immediate attention. So again, to give you a sense of what we're dealing with, here are 3 such unsolicited messages. You can read them as a question about hepatitis B. There's a disturbing question of concerning dead bodies. There's an issue about societal impact. How do we prevent young girls against early marriage and so forth. So basically what UNICEF had set up prior to our involvement was a set of categories. It turns out there's 12 categories: water, health, orphans, vulnerable children, violence against children, and so forth. And you can imagine that there are additional set of UNICEF agencies and other governmental entities that are basically on top of and need to see messages that are filtered according to health, according to, say, social policy, employment, and so forth. And our job is to, in real time, be able to build a classifier. First of all, build a classifier that will accurately route that message to a particular category so that it can be picked up by people on the other side of the interface, if you like, that are responsible for driving impact. Now the good news is that before we got involved, UNICEF Volunteers had actually labeled over 50,000 of these messages, because that's what they need to be able to do. They had to label them so they could route them. So the beauty of it is that we had a nice supervised classification problem because we had these 4,000 labeled messages across the 13 message categories that are involved. It's a challenging problem for a couple of reasons, because first of all, the class labels are highly skewed. There'd be classes that have less than 1% of messages, and there's a large number of messages which are not immediately relevant to any class. So what you'll be seeing here in a moment is the way we sort of evaluate the measure of accuracy in the system is something called area under the curve, under an ROC curve. And the way we look at that is that it's a more useful way of sort of evaluating a ranking mechanism. Because at the end of the day, again, it's an information filtering problem. We want to make sure that we have the most relevant messages at the top of the list. So here's an outline of sort of the analytics pipeline that we built. And what I'll tell you is I'll go into some detail on each of these. Effectively, to give you a quick peek of sort of what the accuracy is that we've been able to generate, is we started with a baseline keyword classifier. That's where volunteers just simply say, if it says AIDS, it's health, if it says this, it's social policy, and so forth. And that has an AUC of about 71%. When we went through these steps that I'll explain in some detail, we basically got that from 71% to 85%. And you'll see some examples of how that actually impacted the actual classification. So here's the sort of the baseline keyword matching, pretty straightforward. So health includes terms that AIDS, HIV, malaria, polio, and so forth. And that's pretty straightforward, particularly around water, because water, anything that mentions water, is a good chance has something to do with water, by the way, is a very significant issue in Uganda, the availability of drinkable water. There are other classes like social policy, which are much more complicated lexicon, complicated discussion, involve words like policy, government, election, so forth, but there's lots of other things that humans would say are clearly part of the social policy discussion. So basically, we then, with that background, then started to build a supervised bag of words text classifier. So that was done just using a standard naive Bayes framework. I'll show you just a quick overview of how we extended that. And what we immediately learned via this text classifier is that if we look, for example, at words for violence against children, that of the 20 words that our model found are most indicative of that particular category, only 7 had actually been identified by experts. So, needless to say, the text classifier is expanding the lexicon, if you like, of the human labeling. So, armed with that baseline sort of text classifier, we got some improvement, basically, a modest amount of improvement in these for naive Bayes, by the way. Now, the next sort of indication of where we needed to work hard was that, remember, these are text messages. So we all text, we all know that our text messages are not grammatically correct, or they're rife with misspellings, etc. And these are kids who, by the way, both English and Swahili are both the official languages of Uganda. The texts we're dealing with are in English. So they're rife with errors. We see texts that, by the way, have no spaces in them. Okay, it's just everything is run on. We can't deal with that. But there are things that we can deal with. So what we basically built was a very straightforward kind of off-the-shelf spell corrector that would basically catch dominant misspellings like suffering and malaria and correct them. The keywords there, suffering and malaria, that's important. People often ask in test messages, well, did you worry about expanding things like BTW? And the answer is no, because BTW is not going to be indicative of a class assignment. It's just the way people text. So this was an important level of innovation because it allowed us to take the accuracy off of the baseline text classifier from 72% all the way up to 80%. Now the next piece is sort of the dominant sort of machine learning innovation, if you like. And what we're doing here in a nutshell is that a traditional approach to sort of text classification, somebody gives you documents as rows and you have labels on them, and you have words across the top from a bag of words decomposition of the text message. So given that the set of labels, you basically learn the weights on words that lead to a prediction of that correct label. That's a very reasonable way to do this kind of problem. The problem is that it leaves behind, so to speak, the human insight that volunteers and UNICEF volunteers understand because they know the lexicon of their categories. They've worked with us a long time. So what we're doing here is something we ultimately call dual supervision. We're using labels that we accumulate from humans that said this text actually belongs in social policy. We're also using information where they say that social policy is defined by certain keywords, government, citizens, and so forth. And what we're able to show, and I'll show this in a moment, is that we can accelerate the learning by taking into account both forms of learning. So how do we do this? This is sort of the one detail slide that I'll show you here. We can talk about in questions. So we start with something that is effectively a naive Bayes generative model. So here the basic idea is to predict a class that has the maximum likelihood according to a traditional naive Bayes-like representation, with one extension I'll show you in a moment that's sort of the key observation. So if you're familiar with naive Bayes, you understand that basically you're trying to estimate parameters of this model that give the best representation in a generative sense of the observed data, in this case the text messages. So we get the prior from the label examples. That's the prior of observing a class CJ. And let me explain that. The probabilities on the right are the naive Bayes independent conditional probabilities, the probability of observing a word I associated with a class J. So our extension here is to basically take, and the dominant contribution, by the way, the dominant approach in naive Bayes is to estimate that from the training data. What we do is we decompose those conditional probabilities into a linear combination of two different conditional probabilities, PE, which is from the labels on the examples that I just showed you, and PF, which is a model that's built, a separate generative model, which is built off the labels on the keywords themselves. The alphas, by the way, typically, they can be adjusted in the learning process. They tend to be close to 0.5. So we then get the conditional probabilities PE are done just as we would normally do that from the examples themselves. The conditional probabilities PF are actually derived from a generative model that I'm not going to talk about in detail here on the labeled features. And this is a piece of work that we actually did in KDD in 2009 and have extended it to the multi-class problem here. Why does this matter? This is why it matters. Here's an example of, as we increase the number of training examples, how much accuracy do we get? If we look at a traditional naive Bayes, it falls well below the dual supervision line. The way to think of this is that if you move into a new domain, by the way, we face this all the time with Watson and going beyond Jeopardy into medical and so forth, is what we want to be able to do is achieve a certain level of accuracy, however you define it, with a minimal number of training examples, because training examples are always hard to obtain in a new domain. In our setting, it could be because we need to go from English to French. It could be because societal problems in Algeria, where the system will be moved, are different than in Uganda. So with dual supervision, we now get up to, on the order, we get up to an AUC of 81, which is modest with respect to the spell correction, but actually this has taken over the entire training set, evaluation set. We actually look at individual classes, in some cases they're 40% higher. I'll show you a couple of examples of that in a moment. Now, the fourth piece, so just to keep track here, we're now down here sort of in what we call re-ranking. So let me start with sort of the observation that we want to make sure that we get high precision at the top of the list. That is, that we say that a message is indeed relevant to this class and requires action, that indeed that is the case. So one of the advantages of keyword matching is that if it does have a keyword match, there's a pretty good chance that it will be accurate. The problem with keyword matching is that it falls short on recall. It will miss many messages, but the ones that it gets typically might be fairly reasonable. So what we've done is kind of a straightforward sort of ensemble model, where at the end we take the method that I sort of walked you through real quickly, and we average it with a baseline keyword model. The idea then is to get the best of both. We want to basically get high precision at the top of the list, courtesy of the keyword model, but still retain the recall that we see deeper down in the machine learned model. And effectively what we end up doing in this case is the word famine, which is a keyword for health, indeed gets us to the top, but we still keep other messages that have been found in the supervised model close to the top as well. And that final step there got us from the 81 AUC of 81 up to an AUC of 85. So let me show you a little bit about the performance of the model, and then we'll talk about deployment. So here is an example of two different classes. Let me start actually down in the lower right there. Again, this is a learning curve. This is the number of messages and the recall on the y-axis. So a good model for a modest number of messages will have high recall. So you want to see these curves in the upper left-hand corner, which indeed we do for water, because water is a fairly straightforward class to classify, because keywords like water and borehole and so forth are typically present in messages in Uganda that talk about issues around water. What's more interesting is sort of social policy, where in fact we see a dramatic difference between the keyword model, the text classifier, and the blue and the red are re-ranking with a couple of different parameters. So this translates to, again, you can see a very significant improvement in the overall learning of the system. Now, why does that matter? So here's some actual text messages, and this is for class water, and this is basically the relevance ordering that we got out of the standard keyword model. Now, the good news is there's a good number of messages that are indeed relevant there, but there's at least of these top 15, 5 of them are not relevant. And one of the problems you can see is, for example, the word well occurs in a message there, has nothing to do with water, but a keyword classifier with the well as a keyword will of course say that it is water. Now, if we take our model that I just described and apply it and look at the top 15 messages that we classify in this training set using that model, in fact, we get complete purity at the top of the list. Everything is relevant, but we find some very sophisticated patterns in here that are sort of representative of water. So sort of a quick slide that shows the overall system in an architectural perspective. This is all in place courtesy of the team at UNICEF. Our piece is on the right-hand side there, where messages are coming in real time, or text messages coming through, being routed in the database. Our text classification system sits on the side and every several hours picks these up, classifies them, and they're delivered out in two interfaces. A public interface, I'll show you here quickly in a moment, and then a confidential interface, which is used by UNICEF, where they can actually see specific messages and the ordering of those and route them appropriately. This is the public user interface that shows something we call national pulse. This is a map of Uganda. There are 111 districts in Uganda, separately color-coded. And what this is showing, I think, over the last week, at the time this image was taken, what the distribution of the discussion is around Uganda. It's somewhat surprising to me. It oscillates a lot. In this particular case, the dominant color, the pink or magenta, is for education. We can also, in the interface, obviously you can click on any district and you can see what are the specific topics, and we've resorted to basically doing a word cloud. We looked at some more sophisticated topic models, but we weren't really seeing things because of the lack of grammatical structure in these texts. We basically ended up using a keyword, a word tag cloud that was, I think, more effective in sort of highlighting what the issues are. Again, this is a public interface, and we can't show the actual messages. So how has this made a difference? So the view that I just showed you, the national pulse, is actually now pushed down to all 386 members of the Ugandan parliament. So they have a parliamentary system, not unlike our House of Representatives, where members of the parliament are aligned with one of 111 districts. So they see actually pushed, they not only have obviously access to the national pulse, they actually see it pushed down to their phones, and they can see what is happening in their particular district. A couple of things that we did catch early on, there was some major flooding. It was actually almost a year ago now in the western part of Uganda. And again, it was very, very difficult sort of to understand the impact of those in real time. And what we started noticing was that there were messages, there was an increased number of messages coming from these districts, and that a dominant keyword was flooding in them. So we actually identified and could sort of use this again a little bit like Twitter in the sense that think of it as a network of distributed sensors, and people are giving you information and you can piece it together. Something that continues to be an issue is sort of the ongoing, so the Congo's western border is shared with the Democratic Republic of Congo, and there's been a number of incidents of civil war in DRC that have caused a number of people from DRC to cross the border into western Uganda and set up refugee camps like you see here. And needless to say, UNICEF, because there were children involved, UNICEF had a very strong interest in understanding what the conditions were, and you reporters, or basically people were joining you report from that particular area and uploading their descriptions of the conditions in these refugee camps. There's a lot of activity now moving this forward. So red stars are basically where it's already deployed. What I've been telling you about is Uganda, but we also have it, as you can see, in several other countries. We'll launch next month, is this month, since we're now in April. And indeed, it is going into DRC, it is going into Nigeria, and we're looking at expanding actually into northern Africa as well, in the countries like Algeria and Tunisia, which, by the way, then introduces a need to process French. And they ask, well, how do we translate this into French? I mean, one observation, it's a lot easier than playing Jeopardy in French, because the fact that you don't need to rely on grammatical structure that's different from French to English. And in fact, the kinds of bag of words models that we build will actually work quite well in a different language, to the extent that a dominant part of the signal is carried in a subset of the vocabulary, which is likely the case here. Also, we can do a straight dictionary translation of the keywords that have been identified in English and translate them into French. Then the remaining question is something we call broadly domain adaptation, and that is sort of, if you like, the distribution, the overall distribution of messages and the way words map to classes could be different because it's a different culture in Algeria than it is in Uganda, and that's an issue that we're starting to deal with now. So let me wrap up here with sort of, since we're talking about innovation here, what I want to do is sort of walk you through a summary of sort of the 4 points of innovation here, because I think one broad takeaway lesson from this work is that in analytic systems in general, it's not always the case that there's just one piece of analytics that makes a difference. It's often because you do things and you tune each step of a multi-stage pipeline in full presence of the other stages to achieve some desired analytical outcome. So again, reviewing what we've talked about here, what is absolutely clear here, and we're in different piece of work, we're doing this with Twitter as well, is we are trying to, if you like, resurrect the original intent of the author. And what is it that they wanted to say, but because of Twitter speak or the use of by maybe non-native English speakers of text messages here was sort of blurred and was obfuscated. So the first step in any kind of opportunity application like this, which is only becoming increasingly true, is the amount of corpus that we generate, particularly from social media, is not structured, like the New York Times or even like Wikipedia. It's a different lexicon, and we need to be able to accommodate that. So spell correcting is essential. The next point is the fact that we as humans, we talk about this a lot now in cognitive computing, we as humans know lots of things. And the challenge in cognitive computing is not like maybe artificial intelligence 2 decades ago. The challenge is to incorporate human learning and human understanding in the best way into a system, so that system can arguably perform as better than maybe the human alone because of scalability, or even by some uninformed system without that human insight. So what we're doing here is basically realizing that it's not that while we were fortunate to have labels on messages, we didn't want to leave behind the insight that humans had already given us, namely that there is a mapping between classes and actual keywords. So it's essential, and I showed you the advantage in the learning curves, it's essential to be able to leverage that. One observation is we talk a lot about big data, and the way I think about big data sort of in a supervised machine learning standpoint is data is growing. We all know it's growing super linearly, exponentially, whatever you like. The amount of labeled data that's available for supervised learning is probably growing no more than linearly and probably sublinearly. and we are being asked, we as machine learners are being asked to move things into new domains without a labeling exercise. So that's why this is critical, sort of a critical innovation here. The third point is sort of the keyword, is sort of that re-ranking at the end, which in a broader context is sort of ensemble learning, where we're learning weights. We have one model, it's a supervised machine learning model, another model, a keyword model. They both have their relative advantages. We are effectively using weights on top of those to replicate, again, high precision at the top of the list and still not sacrificing recall as we go for these message orderings. So again, if we look at this full pipeline with these three key steps, we basically can start from this baseline and go from, as I said, an AUC of 72 all the way up to 85. And while those are just numbers, I mean, if you do this sort of thing for a living, that kind of movement is substantial. And I showed you sort of in the way that we got 100% pure relevance classification of the top 50 messages. That's a very practical instantiation of that level of innovation. So let me stop there and take questions.